This is an introduction to differential equations, and in this video we will be talking about direction fields. So many of our differential equations cannot be solved explicitly or implicitly, and even once we have an implicit solution, finding an explicit solution from that is very, very difficult and sometimes not even possible. So we now turn to something called a direction field, and it is a field of something called slope marks. And this gives us a visual representation of the solution to first order differential equations. So this is a graphical method of solving differential equations. Okay, and these little short line segments called slope marks show the slope of the solution curve at any point xy, and it will also give us this flow of the solutions. So we can also find a particular solution. That is a solution of the IVP. That is a unique solution. That particular solution can be sketched using the direction field also. Now this is a unique solution, of course, if we satisfy Theorem 1. Okay, so let's take a look here. This is our differential equation. So that's our dE, and it is a function of x and y. And this here, right here, this function will give us the slope of the solution at any point xy. Okay, so let's go ahead and take a look at our first example. dy dx equals x squared minus y. That's our differential equation. We have 2 points plotted here. Let's go ahead and take a look at them, and then we'll talk about them and how they flow over here. So let's go ahead and find that, look at that first point 0, 1. And we have dy dx is equal to 0 squared minus 1. And that's equal to negative 1. So you can see a slope mark that has a slope of negative 1. Okay, let's now look at this point here. And why don't I make that a different color? So we'll go ahead and make this point 1, 0. And dy dx is going to be 1 squared minus 0. And that's equal to 1. So a slope mark with slope 1 is located at that point. Now, let's go ahead and look over to the right. This is the flow of solutions that we can actually sketch. So if you were starting with this point here, you could actually sketch a solution, whoops, that looks like this. That's not good. Let's try one more time, like that. So that is why these follow these trends, this flow, as you can see, and the solution passing through that point 1, 0 will also follow the same flow. Let's take a look at 2 points. Let's try negative 1, 1. Okay, so there's a point negative 1, 1 here. I will go ahead and make that one pink. So we have negative 1, 1. And here we have dy dx is equal to negative 1 squared minus 1, and that's equal to 0. So we have a horizontal slope mark, and you can see it right here. There at that point, negative 1, 1. Okay. Let's go ahead and look at our next example. dy dx is equal to negative 2y. So we have 2 points here. Let's take a look at them. That is 0, 1. And as you can see, this DE is only dependent on the y coordinate. So for every x coordinate, we will have a different slope mark. But for every y, as you can see, when y is equal to 1, we will always have a slope mark with what? -2 times 1 with slope of -2. So you can see here that all of these slope marks have slope -2, and that's because y was equal to 1. Okay? And it didn't matter what the x coordinate of that point was. So you could almost say, okay, how about -1, 1? And that would be about right here. And of course, it's the same thing. -2 times 1 equals -2. So again, we have that slope mark of -2 with slope -2. Okay, so we now go and look at this next point. Let's use purple and just look at this last one, and we have that point is 1, 0. So we have dy dx is equal to -2 times 0, and that's equal to 0. So that has a slope mark of 0. Okay. Because for this differential equation, we have -2y is continuously differentiable. For all x and y, we can now enclose any point in this rectangle. So any point x, y in this rectangle of continuity. So this is what we're going to call a rectangle of continuity. And this came from the uniqueness and existence theorem. And basically what it says is that this equation has one and only one solution passing through each point. So we conclude that we have one and only one solution passing through each point. Okay, x sub 0, y sub 0. Okay, so we will have a unique solution. So we actually have a solution here passing through that point, and that of course is y equal to 0. Okay, let's take a look at our next example. Dy dx is equal to the opposite of y over x. We have 2 points that we're going to take a look at. So let's start with 0, 1. So dy dx is equal to the opposite of 1 over 0. And here, dy dx is undefined. Okay, let's take a look at them. We're going to talk about that in a minute. Let's take a look at this point 1, 0. So here we have dy dx is equal to the opposite of 0 over 1, and that is equal to 0. So we have a horizontal slope mark there. We could go ahead and just put that other one there. Here on this slope field, you can see that all solutions approach y equal to 0 as x approaches infinity. And you can also see that here. Maybe if you had this point here, you can see this, whoops, coming down. Also, and you can see these solutions coming through here, and you can sort of see this flow. So we are approaching 0. Basically, no solution can make it across this x-axis. I mean the y-axis. So no solution can cross the y-axis. So this is very interesting because as you can see here, as these solutions get very, very close, as x gets very close to 0, y approaches infinity. So, and you can see that right here. So if we have dy dx is equal to the opposite of y over x, and as x approaches 0, as x gets very, very small, your y, dy dx gets huge, and those solution curves approach infinity. So it's very, very interesting. Now, let's talk about this rectangle and the existence and uniqueness theorem. If we exclude any point, any non-zero x value, so if we have a non-zero x value, can enclose this rectangle of continuity and guarantee a unique solution for every x and y value. Okay, let's look at this next example. Dy dx is equal to 3y to the 2/3 power. Now, this is a very interesting differential equation because what we have here is two solutions passing through this one point. So at 2, 0, there are two solutions passing through. We can go ahead and do our thing. We can go ahead and view using the flow of the slope marks in the direction field to find that one, and we can easily navigate this solution. But again, we do not have the uniqueness for one solution passing through every point. And this is because it did not satisfy, this DE does not satisfy the uniqueness and existence theorem. So basically, any rectangle containing the point, whoops, I meant there is no rectangle, containing the point 2, 0, where f and the partial derivative of f with respect to y are continuous. Okay, let's look at our next example. This is the logistic equation for the population P in thousands at time T of a certain species, and that's this differential equation. So let's just take a look at this. Let's take a look. We'll just make a few notes before we even answer the question. Let's note that when P is equal to 2, which is 2,000, we have dP dt equal to 2 times 2 minus 2, and that's equal to 0. So dP dt is equal to 0, which means P is constant. That solution is constant. Now let's look when P is greater than 2. If you have dP dt, if you have a value greater than 2, let's just try. Let's see. For example, you could use 3. You could see that dP dt is going to be less than 0. And that means that the dP dt is P is decreasing. And if P is less than 2, think of a number maybe 1, dP dt is going to be positive, which means P of t is increasing. Now, keep in mind that this solution here is P equal to 2. And so that's where dP dt is equal to 0. And here, if we have a population, let's say of 4, or let's say of 3.5, that P of t is going to be decreasing. Of course, we can't cross P equal to 2. And let's say we started here with a P less than 2, we will be increasing, okay? Okay, so now let's go ahead and answer the question. So in part A, if the initial population is 3,000, so if, oops, let's just write it. So we have P of 0 is equal to 3. So we'll be right here. We will be decreasing, but we will never go below P equal to 2. So if the initial population is 3,000, what can you say about the limiting population? You could say that the limit as t approaches infinity of P of t is equal to 2. So the population is of 2,000 is the limiting population. Okay, let's go ahead and look at B. Can a population of 1,000 ever decline to 500? Well, since P equal to 1,000, let's just go ahead and use 1. So if P is equal to 1, that is less than 2. So therefore, P of t will be increasing, but never reaching P of t equal to 2. So we cannot cross the solution curve at P equal to 2. We will never reach that. So that answer is no. Okay, and in part C, can a population of 1,000 ever increase to 3,000? So if we are here at 1,000, we will be increasing, but we can never cross that P equal to 2. So the solution curve will never reach P equal to 2 or cross it. So P of T is increasing, but will never reach P of T equal to 2. Therefore, P will never increase to 3,000. Okay, let's take a look at an autonomous equation. So we note that the direction field in the previous example has slopes that do not depend on t. That is, the slopes are the same along each horizontal line. So as you can see here, let's just take a look before we look at the problem. Along this horizontal line there, and let's say along this horizontal line there, we have all the slopes are the same. Okay, and so we call this an autonomous equation. So here we have that for a differential equation, the function is only dependent on y, which is our dependent variable. In sketching these direction fields can be a bit tedious. Using what we call the method of isoclines will greatly help us sketch these direction fields. And as you can see here, this is a previous example. All of the slopes depend on P, our dependent variable. So they are independent or not dependent on T. So let's introduce this method of isoclines. So basically this will help with our hand sketching of direction fields. And an isocline for a differential equation is a set of points in the xy plane where all of the solutions have the same slope dy dx. Okay? So let's just jump right into an example and see what we have here. So our first example is dy dx is equal to x plus y. Here, the isoclines are straight lines. So you could say x plus y equals c, or you could say y equals the opposite of x plus c. And of course, c is any constant. So you can see here over in this first sketch that we have all of the lines, rather isoclines, graphed for y equals the opposite of x plus 1, y equals the opposite of x plus 2, and here, of course, I'll do this one in green. This is just y equals the opposite of x, since there c is 0. So once we have these isoclines sketched, we then will be able to see, once these isoclines have these hash marks showing, that along, let's go ahead and use this one, y equals the opposite of x plus 1, every slope mark on that line has the same slope. And then you can go ahead and see that for this next one here. We could use this one for y equals the opposite of x plus 2, of course, because that's 2. And all of these along that line, all of the slope marks have the same, are the same. And this is what creates the direction field. Now, the isoclines don't have to be straight lines. We do want to make it known that this can become very complicated. And so it may not be the method. So, and now we can see some of the solutions. This is for 0, 1, that point 0, 1, and the point 1, 0. You can see how they will follow this. So each one of these are called isoclines. And that concludes this lesson.